Section 8.4, Mathematical Induction. Principle of mathematical induction says let P of n be a statement involving a positive integer n. Remember, our subscript tells term numbers we're talking about. So we're talking about some statement involving a finite number of integers. Principle of mathematical induction tells us that if P of 1 is true, which means when we plug 1 into our formula, that holds true, and the truth of P of k implies the truth of P of k plus 1 for every positive k. Remember, our k term, which is what P of k represents, and our P of k plus 1 term, k plus 1 comes immediately after our k term. So what we're saying here is that if we can assume that P of k is true, and we can show that that assumption implies that k plus 1 is true, then we can say by the same implication that if P of k implies P of k plus 1, then P of k plus 1 must imply P of k plus 2, which must imply P of k plus 3, and so on, and that's where the induction comes in, and therefore P of n must be true for all positive integers n. So steps in our proof. And these are the exact steps that you will need to follow for the quiz and the test. First thing, you will write down what you are doing, and then you will actually do it. So our first step is to show the formula is true when n equals 1. You will write that down, and then you will actually plug 1 in and show that the formula does work when n equals 1. Step 2, you will write this down. Assume it is true when n equals k, and then you will write down that step. So again, what you are doing, then do it. What you are doing, then do it. Step 3 has two parts. We want to add the k plus 1 term to the kth sum. There's one part. And then we want to substitute the term number k plus 1 into the kth sum. And our goal is to show that those two expressions are equal. Once you show that these two expressions are equal in part A and B, your conclusion will be therefore, by the principle of mathematical induction, P of n is true. So whatever statement you set out to show is true, you will have proved by the principle of mathematical induction if you can do these three steps. So the first thing we need to do here is get used to plugging in k plus 1. Remember, when we have an expression like this, to find a specific term, we put the term number into the expression. So in this case, our P of k statement is that the sum of the first k integers is k squared times k plus 1 squared over 4. We want to find P of k plus 1, so we want to find that next term. We're going to put k plus 1 in every place that we had k. So we're just plugging in the term number in to evaluate the expression. Now for these problems in the homework, you do not need to FOIL things out, simplify any simple addition, things like that. Otherwise, you can leave it in this form right here. Will match up with what the answers look like in the book. Second one, we're going to do the same thing. 1 plus 5 plus 9 plus. That means this whole thing right here, since this is the sum of the first k integers, this represents our kth term, that whole thing. Obviously, that has not been simplified as much as could be, but we can still use that to find the next term. Put k plus 1 in. We get 4 times k plus 1 minus 1 minus 3 plus 4 times k plus 1 minus 3. Begin simplifying. The ones cancel here. We're just left with 4k minus 3 plus 4k plus 4 minus 3. Add like terms. We end up with 8k minus 2. Part C. Again, plug in k plus 1. K plus 1 plus 3 is less than 5 times k plus 1 squared. K plus 4 is less than 5 times the quantity k plus 1 squared. Finally, D, same thing. Put in k plus 1. 3 to the k plus 1 is greater than or equal to 2 times k plus 1 plus 1. And that, in essence, is what you are going to be doing in that third step of your proof. So now looking at an entire proof here. Prove using the principle of mathematical induction that the sum of the first n integers, 1 plus 3 plus 5, so on, up through the nth term, which is 2n minus 1, is the same thing as just taking the term number and square it. In other words, if I want to know the sum of the first three terms, well, I can just add them up. 1 plus 3 plus 5 is 9. What this formula is telling you is that if we want to find the sum of the first three terms, we can simply take the term number and square it. What does 3 squared equal? 9. So we can see that it does work for the first three terms. Our first step in the induction proof is to show that it works when n equals 1. So we want to show the formula is true when n equals 1. So now we're going to go ahead and do that. Sum of the first term, put 1 in, 1 squared equals 1. That is what this first term equals. So we have told what we are going to do, which is show the formula is true when n equals 1. We've then showed that. There's step 1. Step 2, assume the formula is true when n equals k. So we have the same formula, but now n is equal to k. So the sum of the first k terms, 1 plus 3 plus 5 plus 2k minus 1 equals k squared. There's all of step 2. So there's 4 points. 1 point in step 1 for telling what you're going to do, 1 point for showing what you're going to do. Step 2, 1 point for telling what you're going to do, 2nd point for showing what you're going to do. Now the third step. We want to take the k plus 1 term, and we want to add it to the kth sum. So what we are doing here, essentially, is finding this k plus 1 term, which we know comes right after this term. And if we add it to this side, that means we have to add it to this side as well. So we're taking this kth sum, which is k squared. That's the sum of the first k terms. And we're simply adding the next term to both sides to keep this equation equal. So our k plus 1 term is going to be 2 times k plus 1 minus 1. So we're using this expression right here. And we're simply plugging in the term number. And now to that, we need to add the kth sum, which is given right here. That's the sum of the first k integers. Simplify that expression. We get 2k plus 2 minus 1 plus k squared plus 2k plus 1. Now we need to do part B. Part B, well, we know that this formula is telling us that we should just be able to plug the term number in to get that same sum. So now we're going to put the term number into our sum. So we want to take our k plus 1, and we want to plug that directly into our kth sum. So we get k plus 1 quantity squared. FOIL that out, k squared plus 2k plus 1. And we see that these two things are equal. And what we have just shown, since we are assuming that this step right here in 2 is true, that the sum of these k integers does equal k squared. In the step A, we just added the next term, the k plus 1 term, to both sides. So we took the k squared and added the k plus 1 term. We got this sum. And over here, we just plugged the term number directly into the sum, and we got the same thing. So we know the formula holds true for that next term. So now by induction, well, we can say, well, if the k term implies that k plus 1 term is true, now the k plus 1 term implies the k plus 2 term is true, and so on. So our fourth step now is therefore, by the principle of mathematical induction, that means that it has to be true all the way up through the nth term. And there's the final step of our proof. Last one, I'm going to start with the exact same steps. So these first two steps will never change. You're doing the same thing every single time. Third step, you're doing the same thing every single time. Obviously, a little bit different algebra work that you're going to have each time. So step 1, show the formula is true when n equals 1. So the sum of the first term. Plug 1 into our formula. 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. We get 1 times 2 times 3 over 6, which is 1. And that is what this first term, 1 squared, also equals 1. So we've shown that it's true when n equals 1. Step 2. Assume the formula is true when n equals k. So that means the sum of the first k integers should equal 1 squared plus 2 squared plus 3 squared plus k squared would be equal to k times k plus 1 times 2k plus 1 all over 6. Third step, part A. We want to take the k plus 1 term and add that to the kth sum. Well, our k plus 1 term we know comes right after this. Plug the term number in to find the value. So our k plus 1 term is going to be k plus 1 squared. To that, I need to add the sum of the first k integers. Sum of the first k integers is given by this formula right here. K times k plus 1 times 2k plus 1 all over 6. Now we have some algebra work to do. FOIL this out. We get k squared plus 2k plus 1. Begin multiplying this out. We get k squared plus k times 2k plus 1 all over 6. Continue simplifying so that I have one fraction here. I'm going to multiply this 6 up to all of these first 3 terms, so I get a common denominator. 6k squared plus 12k plus 6. FOIL these two together here. We get 2k cubed. Outer k squared. Inner 2k squared. Last plus k. And now finally add like terms. And we end up with 2k cubed plus 9k squared plus 13k plus 6 all over 6. So that's what we get when we add one more term to both sides here. Step B now, we want to put that term number, the k plus 1 term, and we want to plug that directly into our kth sum. So when we go to plug this in, we have k plus 1 times, put k plus 1 in here, we get k plus 1, which is k plus 2. Put k plus 1 in here, and we end up with 2k plus 3. Begin the algebra work here. FOIL the first 2 terms together. When we FOIL those together, we get k squared plus 3k plus 2. Continue multiplying. I now need to distribute this 2k through to everything. We get 2k cubed plus 6k squared plus 4k. Do the same thing with this 3. Distribute it through to everything. 3k squared plus 9k plus 6 all over 6. And finally collect like terms. 2k cubed plus 9k squared plus 13k plus 6 all over 6. We see that those two things are equal. Therefore, our last step, therefore, by the principle of mathematical induction, 1 squared plus 2 squared plus 3 squared plus n squared does equal n times n plus 1 times 2n plus 1 all over 6.